All right. I just realized there was one other item I had wanted to show you on the level crossing information that was specific to Israel. That I just so let me not forget. I did want to show that. So um, let's see if I can make that work. Okay. So this is this is an announcement that was made back in 2017 when Israel Railways officially joined the International Level Crossing Awareness Day program. And one of the, I'm not going to go through it. You're welcome to read this on your own. But what I did want to show you here is that there was a whole bunch of material that was put together in Hebrew. Let's see if it comes out here. There we go. Okay, so this is the kind of material that this is among the other type of information that's available in Hebrew for level crossing awareness. This is put out obviously by Rakhevet Yisrael and the Ministry of Transport here. So, okay, so that's there. Let me stop sharing this and go, and let's start talking about turnouts. Okay, can you all see my slides? Are my slides visible to everybody?
Yes.
Yes.
Okay. All right. So we're going to talk about turnouts in general, to include derailments and turnouts. For obvious reasons, I like this particular picture. Not quite what happened, that common, but basically what you see happened is that the leading bogie was going down this track, and the trailing bogie more than likely got caught up in the frog over here. And instead of following the leading bogie down the diverging track, probably because the guardrails were not, in fact, I don't even see the guardrails, proper guardrails in this particular picture. So it looks like they may not even have proper guarding in here. So the trailing bogie went down this track, and it's obviously not going to go very far before you get that kind of situation. Okay, so we're going to start off by talking about a couple of accidents in the UK. Again, I like UK accidents when I talk about Israel, because Israel has a very, Israel Railways heritage is British, and so there's for good, bad, or indifferent, the Israel Railway heritage is heavily British, or used to be heavily British. So there's a lot of commonality. So this was a very famous accident that occurred in a place called Potter's Bar. That's, believe it or not, the name of a town in England that happened in 2002. So this was a train that was traveling on the British rail main line from King's Cross, London. So it's going from London to a place called King's Lynn, and it derailed at just south of the Potter Bar station. I'm going to show you some videos of this as well. This train actually became the fourth vehicle actually derailed and literally slid up into the platform and got stuck into the canopy of the station. 7 people were killed, 70 injured. So this was a real messy one. Again, I'll show you some video in a moment, but you can see what happened here. That this is the station platform. This is the canopy of the station, and this is the the train, the fourth car that derailed. Again, you can see another picture of it. That was the end that was stuck under the station canopy right over there. And there it is again. Okay, so in this particular point, in this particular accident, there was a malfunction at this point. And I keep telling you that it's really, really, really important to understand what causes those accidents so you can examine other cases and see if there are other accidents waiting to happen. So in this particular case, after this accident, they found the cause, which was a problem with the switch points. There were 9 other switches nearby that were examined, were found to have similar but less serious defects. So the point failed in such a way that the train was basically pulled. It went in between the switch rail and the stock rail. And so as they got closer, the train actually, the car actually just popped off the track. Okay, so what happened here, in fact, let me show you what happened here. There was actually some bolts came loose. And the bolts came loose from the right-hand end of the rear stretcher bar. So the stretcher bar is the bar that connects the left switch point with the right switch point. So that makes sure that when you turn the switch moves all the way in one direction. Both switch points move all the way in the one direction and all the way in the rear another direction. If for some reason the stretcher bars are not connected properly, then one switch rail can move and the other switch rail can stay the same, and you can have a situation where you're going down the wrong end. So in this particular case, there was the stretcher bar bolts came loose, were not found by inspection, and so not only was there a question of poor maintenance, but also poor inspection. Well, let's face it, this should be pretty obvious in a visual inspection. What happened to the inspection here? So this, and this point in time, when this accident had happened, there was a maintenance contractor for that section called Jarvis. That's a British company that was responsible for all the inspection and maintenance. So again, there was a big question here. What happened? So let me just real quickly show you a quick video of that. It doesn't show the accident, but it shows you the after effects. So I just want to make the point. Where are we here? Let's come back here. Let's come back here. Hopefully it's going to work. There it goes. So there's no sound on this particular one, but you can see.
We can see the video.
You cannot see this?
No.
Okay. Can you see the video? Can you see the video now?
Yes.
So what happened in this particular video, in this particular accident, there was, as I showed you, there was the bolts came loose. There was actually a fracture of a bolt, in fact, and it came loose, and
and I just heard the most enormous explosion.
The noise of it was just phenomenal. I mean, you just cannot believe what it sounded like. The whole building here shook.
So you can see that leading into the switch is a fairly complex interlocking, and remember I told you it was a lot of times you see these kinds of buckles are after the result of the accident, just like we saw that in the Israeli derailment that I showed you earlier in one of the classes. Okay, so let's go back. Do you all see my slides again?
Yes.
Okay. All right. So you think that was such an unusual accident, you know, they corrected the problems and they would never see a accident like that again. So that was 2002. 5 years later, in a place called Grey Rig, there was a intercity mainline track, a mainline train running from London to Glasgow, Scotland, on what's called the West Coast Main Line. So that's the main line that runs along the west coast of England from London north to Scotland. So this particular train was traveling at about 155 kilometers per hour when it derailed. This happened in a very inaccessible location. So in this particular case, it took 500 rescuers, 12 ambulances, 5 fire engines, 3 search and rescue helicopters, and 4 mountain rescue teams to basically get through, to get everybody out and get all the people out of that particular accident. So one of the carriages fell down the embankment. And then the second one went down the embankment. Again, it was another messy accident. And again, it was caused by a faulty set of switch points. This was not a manual switch. This was a mainline operation. So the switch was controlled from the dispatching center, which was located in a place called Lambrig, which was down the road, not visible, but this was a mainline, fully automatic switch that was operating on the West Coast main line. It turned out afterwards that the maintenance contract, again, it was under a maintenance contract. The inspection never took place. The switch inspection never took place, and so they never found that they didn't detect that problem when it happened. So again, you can see London to Scotland, Glasgow happened sort of in the middle of nowhere over here in a place called Grey Rig. You can see what happened. It was very, very remote territory out here, but you can see the engine, a couple of cars, all down the embankment. So cars 1 through 5 derailed and overturned. Car number 6 just derailed, and then 7, 8, 9 didn't. Nothing happened to them. They just stayed on. They were stopped in time. So again, you know, this is the derailment scene. Okay, so again, here we got a better picture, so we're allowed to do that. All right, so again, very quickly, these are our stretcher bars, also called gauge bars or control bars, number of different names by now that you know, but they're basically in the United States, we call them switch rods, but they're the bars that connect the 2 switch points together. Or so, if you want to use a British term, the 2 switch blades together, and to make sure that they move together, so that when like in this particular scenario, this is open, so you go down the track. So you're going to go down the track here, and then this is closed, so you're going to go down again the same track here. So you're going to go through the straight leg of the switch. So again, there are my stock rails. There's my gate, my switch rods or stretcher bars. You can see that in this particular case, there were 3, or 1, 2, and 3. In this particular case, there was damage to the number 1 stretcher bar over here. So what ended up happening is because this bar was damaged, instead of this opening, this closed. So we had a scenario that looked like this. Now you can see this is, again, this is not a manual switch. This is a mainline remote control switch. So it's a, so instead of it looking like this, where the train can simply go down the straight leg because I'm open here and I'm closed here, what happened is this stretcher bar, when it moved in this direction, when it reversed the switch, it failed to pull this one over. So this switch blade remained closed. So you have a scenario where I have a closed switch blade here and a closed switch blade here. So along comes the train, and this wheel is going down this direction, and this wheel is going down this direction. And after a while, this is just converging, and the train's going to pop. So, you know, this is a classic derailment. So again, this is what the, and this by the way is was a fairly sophisticated high-speed switch. So again, you can see the stretcher bars, first, second, third, and that's what connects the two switch blades, the switch points, and to each other and to the switch machine. So okay, so there was an actual failure. So the condition of the stretcher bar arrangement, and particularly this stretcher bar, was such that it did not pull this switch blade over. So the stretcher bar components had been found to be disconnected. In fact, of the three bars, one was not in position. That's the first one. The second one had nuts and bolts missing, and then there was a third one that was fractured. So this one was not in position. This one had missing bolt nuts. This one had a fracture. It was a lousy situation altogether. So the obvious question was, what happened to inspection and maintenance? Again, this is a failing in inspection and maintenance. Again, shows the importance of it. They did run a inspection train, and this is their track recording car, did run over the train not that much before the accident, but it does not inspect the condition of the switch blades. It makes a video that they were able to look at later, but at the time of the inspection, videos are not usually inspected on a video train. One of the areas of technology that's being worked on right now is artificial intelligence that can look at video recordings in real time. And maybe that can be found in the future. But right now, that technology doesn't exist. In this particular case, there was about 4 million pounds worth of damage. One person was killed, 22 people injured, etc.
Professor, how frequent they supposed to inspect this?
And track like this, they should be doing a manual inspection twice a week. Twice a week, somebody should be walking across that switch and looking at it, or either walking across it or driving across it at a very slow speed so you can see everything.
Thank you.
That's typical manual inspection standards for switches and tracks. Plus, there's supposed to be a detailed, comprehensive switch inspection, usually once a month.
Yeah.
So twice a week, you walk the inspection, and quite honestly, you should be able to see missing bolts in a walking inspection. But once a month, there should be a comprehensive switch inspection where, among other things, they actually move the switch points.
Of course, a comprehensive maintenance
Right.
operation. Yeah.
That's right. Where you move the switch points and you see what happens here.
Mm-hmm.
Okay, so switch derailments are, again, a major category of derailments. We're not going to go through a lot of that. When typically, if you recall, I'm sure you all remember all the numbers I threw out you at the lecture 3 weeks ago. But basically, switch derailments are sort of number 3 in the track causes. So of all the track caused derailments, usually you have track geometry, then you have rail related ones and rail and joint related ones, and then you have switch derailed ones. And when we look at the causes within the switch derailments, what we find is that the switch points, problem with the points, also called the switch blades, are the biggest cause of derailments. That we see consistently.
What is a switch stand, please?
Switch stand is a switch machine. Usually the switch stand refers to the manual version, where you can somebody can go over and physically move the points manually, from a handle in the switch machine. But it also refers to, in this particular case, there is no handle here. This is fully automatic, but this is still considered to be the switch stand. You can see the frog area is nowhere near as major a cause as the switch point area. Even though frog derailments can be very expensive. Okay, so let's talk about, let's do a refresher of turnout terminology. Then I'm going to show you a couple of videos which give you an overview of the switch, and then we'll talk a little bit about switches and different types of switches, etc. Okay. So typically speaking, a switch is okay. So again, terminology. In some parts of the world, this whole system is referred to as a turnout. Can you all see the yellow that I'm writing in? Is that all visible to you?
Yes, we do.
Okay. In other parts of the world, this whole system is called a switch. And as usual, there's going to be some confusion in terminology. So typically, a turnout is broken up into 3 parts. It's broken up into what's referred to as the switch or the switch point, which is the movable portion of the turnout. The frog area, where the 2 rails cross each other, and the closure, where you have 4 rails that connect the switch and the frog, or there are 4 rails, 2 of which connect the switch and the frog, and 2 of them which go straight through. So you have your switch points, which, if I can go back to the picture, let's see, do I have a picture here? Let's see. Good. So you have the switch points, which move together. And they, in this particular scenario, again, the train is going to go down this track because the wheel is going to go down here and go down this open point and go there. But if I close the switch to the opposite direction, if I close this here and I open this here, the switch is going to go down that direction. So again, you have the switch point, you have the switch length, which is the distance from the top of the switch point to the heel block over here. So your switch point length goes from here to your heel block. And the switch moves around the heel block. So there's no movement of the switch point on the other side of the heel block. We have the switch rods or stretcher bars, which you can see in this particular picture over here, and you can see it also over there. So that's what connects them. Depending on the size of your switch point, it will depend how many stretcher bars you have. You always have a minimum of 2, 3, 4, for very long switches. Excuse me. Very long switches, you may have a 5th, but usually it's 1 to 4. The length of the switch point is determined by the angle of the switch, which determines the allowable speed. So the smaller the angle, the greater the speed, the greater the length. So basically a high-speed switch is smaller than a low-speed, is physically larger than a low-speed switch. And in fact, the overall length of the switch is referred to as the lead, is the distance between the switch point and the frog. And that's the lead length. Okay, we have the switch stand or switch machine, which I can't quite see in this picture, but I suspect it's off on, probably on this side over here. And that's really those are your key switch components. Of course, your switch ties, etc., and your braces and everything else. Again, your lead length is the distance from the switch point to the frog. Okay, when we get to the closure rails, we have 4 closure rails. Okay, so again, here's my switch point. Here's my switch point. I have 4 rails that go basically from the front of my switch to the 2 tracks outside, right? Because I go from 2 rails here to 2 rails on this direction, 2 rails direction. That's 4 rails. I have my curved closure rail, which goes from this switch point to the frog. I have my straight closure rail, which goes from this switch point to the frog. And then I have my 2 stock rails. I have my straight stock rail and my curved stock rail. So again, going back to this drawing, I have my straight stock rail, I have my bent or curved stock rail, I have my straight closure rail, and I have my curved closure rail. And by the way, notice the switch point, there's a curved switch point and a straight switch point, which you saw in the other picture as well. Then in my frog zone, I have my frog itself, which is where my 2 rails go across. So this is, you can see the curved closure rail and the straight closure rail meet at the frog and they cross. And how do you allow a wheel to cross? You have an opening. So you have an opening down the straight side and an opening down the curved side. How do you prevent the wheel from going down the wrong direction? So let's say, for example, let me clear some of this mess so we can see this better. So let's say I want to go down the diverging leg, the curved leg. So it's a right-hand switch and I'm going down the diverging leg. okay? I have one wheel that's coming down here, and I have a second wheel that's coming into the frog. Well, what's going to keep that? What's going to make sure that that wheel goes down this opening and not that opening, since they're pretty close to each other? What guarantees that is this
The guardian.
guardrail. Say again?
The guardian rail.
Yes, exactly. The guardrail. Exactly. This guardrail right over here grabs this wheel and makes sure that the other wheel goes down the diverging leg where it's supposed to. Similarly, if I was going down this leg, then this guardrail grabs this wheel and makes sure this wheel goes down this leg over here.
So you always need to measure the gauge between the
Yes.
guardrail and the frog?
I'm going to get to that. There are actually 3 gauges that are involved, and they're absolutely critical. And if the guardrail gauge is wrong, let's say the guardrail gauge is too wide, and it allows the wheel, allows this, if it's too wide, if this guardrail is too far out, for example, and it allows this wheel to go down in this direction, you have a wheel going down here and a wheel going down here. That's not going to, and you're going to end up with that picture I had in the front. Remember the picture I had in the front with one half of the
Yes.
locomotive down one end of the track and the other end of the track on down the other of the track. That's exactly what will happen.
Okay.
And again, you can see in this picture, you can see the guardrail. You can see the guardrail. Again, you can see the guardrail here. You can see the guardrail here in the frog opening. By the way, anybody know what this is? You Metro people? Anybody know what this is?
Third rail?
Third rail, exactly. For heavy rail metros, they get the power from the third rail. Now, putting together a third rail and a switch, as you can imagine, is a little bit of a mess because you got to make sure it goes down each direction. So in fact, there's very often a gap in coverage. You can see here, there's a gap in coverage. So you got to make sure the gap is less than the length of a car or two. So you make sure you don't have you don't run out of power and your metro train stalls along the way. The third rail, by the way, is underneath here. This is the protective cover or cover board for the third rail to make sure you don't accidentally, a maintenance away worker or a trespasser doesn't accidentally step on that and get electrocuted. Because yes, if you step on a third rail, you will get electrocuted. Although this is one of the cases where the movies actually do have it right, that you get it. By the way, you can see the switch machine just off in the corner over here as well. Okay, again, straight closure rail, curved closure rail, straight stock rail, curved stock rail. By the way, notice these switch timbers. Let's go back over here. This is a good way to see it. Take it, basically you have your switch timbers need to be fairly long because they have to go across all 4 tracks before they finally separate over here. And then you have the extra long switch timbers in this particular case, where if you have a third rail, you can see these are your third rail mounting switch timbers as well. That's why these are extra long over here. Okay. How do you which side is the measurement side of the turnout that you take all your gauge and alignment measures? It's this. So what you see here, you have a left hand. So you have the left hand turnout over here. You have a left hand. So you have the diverging leg over here. You have the straight leg over here. This side on the right side is what's called the line side of the turnout. This is where you take all your measurements. So you're measuring gauge, you're measuring from this distance. You're measuring you're locating your switch point, your closure rails, your Everything else, you're always measuring. When you measure your geometry of your turnout, you're measuring your geometry of your turnout from that particular side, the line side. Okay, so you have three basic configurations of turnouts. You have the right-hand turnout. So here you got the straight and the diverging is to the right. The left-hand turnout where the diverging is to the left. And an equilateral turnout where there's no straight and you only go to the left, you go to your right. So anybody want to tell me why would I ever want to use an equilateral turnout? What's the purpose or the advantage of an equilateral turnout? Anybody want to guess or tell me or no?
When it's an equal number of trains.
Exactly.
To each direction.
Exactly. Because in a traditional turnout, the dominant traffic is going through the straight leg, and that can go in maximum speed. And because you're now going through this whole curved closure rail, curved switch rail scenario, you have to slow down. I mean, let's look through here. You're not going to go through this leg at the same speed you're going to go through this leg. So you're going to slow it down. What speed? It's a function of the turnout angle and the turnout length. We'll talk about that in a few moments. But so if I have the majority of my of my traffic going through here, then I use a right-hand or a left-hand turnout. But what happens, as Rima said, if you have half your traffic equally going through this leg and half your traffic going through this leg, then what you want to do is you sort of compromise. By doing an equilateral turnout, you cut your switch angle in half. So although both sides have a switch angle, the switch angle is half the switch angle of a traditional right-hand or left-hand turnout. That means you can go through both these legs at faster speed. And since both are equally important, you need to have the same amount of speed on each. So you use an equilateral turnout to make sure that you have the maximum possible speed equally through the two through legs of the turnout. What speed is again? It all again is a function of the turnout size. Why can't you put out, what determines the turnout size? Very often, sometimes it's what speed you put a turnout side to match your speed. Sometimes it's a distance. For example, if you're in a metro and you're building and you have to put a switch in underground in the tunnel, sometimes you have to force that switch into a given location. You don't have unlimited amount of space in a tunnel somewhere. And so as a result, you sometimes have to control your speed as a function of what you can fit in there. Ideally, if you're designing it from scratch, you want to design your switch to match your speed that you want it to operate on. And so you pick a turnout side to match the speed that you want to go. But that's not always, it's not always possible, particularly in metros, but also in railways as well. Sometimes you're putting a switch into an industrial siding or a yard or some strange location where you don't have a lot of space, and you're forced to live with what you have. Okay, just continuing with terminology, a facing point move is a move in this direction where I'm going into the switch point. That's referred to as a facing point move. A trailing point move is as I'm coming from the frog to the switch point. So you can see I have two options here. I can be coming from the through side or from the diverging side. In either case, it's a trailing point move. And of course, you got to make sure your switches are properly aligned for a trailing point move as well. For example, if you were trying to come in from this side with the switches aligned in this direction, you're going to have a slight problem. Okay, so before I go further here, I have two videos I want to show you that sort of give you an overview of switch, of turnout and switch design, and then we'll come back here. So let me stop sharing this. And come back here. Okay. Is everybody seeing my screen share?
No?
No, I don't see the video, we see only browser.
Video.
Say again?
We see in your folder.
You saw my folder?
Now we don't.
Can you see the video?
No? Yes.
Yes, yes. Yes.
Okay, this is another one of those network rail videos that I like so. So again, you're gonna hear the British
Switches
terminology.
and crossings play an essential role in connecting the rail network.
Make sure you hear it as well.
We use them to guide trains from one track to another and to enable lines to cross paths. Put simply, they're the junctions that allow us to create a multi-lined, multi-routed rail network. At Network Rail, we own over 20,000 switch and crossing units. They come in many different shapes and sizes, and all are made to measure for their specific location. To understand how switches and crossings work, we first got to look at the wheel-rail interaction. Train wheels move along the rails guided only by the pound-coin-sized area of wheel that sits on the railhead. The wheel rim, or flange, doesn't normally touch the rail. Flanges are only a last resort to prevent the wheels becoming derailed. A switch can guide a wheel in one of two directions. A crossing creates a gap in the rail for the flange to pass through.
So that's a frog.
This is a switch. Also known as a point, it's the moving part of the switch and crossing layout, and is made up of two long blades which can move across to guide the train one way or another. This is the switch rail, and this is called the toe. This is called the stock rail. It's a non-moving part of the switch. The two switch blades are fixed to each other by a stretcher bar to ensure that when one is against its stock rail, the other is fully clear and will provide room for the wheel flange to pass through cleanly. This is a crossing.
Also
It's
known as
the
a frog.
non-moving part of the switch and crossing layout that allows a train to pass in either direction once the switch has been set. This is the nose of the crossing. Either side of the crossing area, wing and check rails are provided to assist the guidance of the wheel sets through the crossing.
Check rails are the guardrails.
Crossings can be either fabricated, made up of two machined rails joined together, or they can be cast as a single unit. Modern crossings are now cast from manganese steel, which is an advanced alloy that gets harder with use. This is an important property, as the nose of the crossing can take high impact loads as train wheels pass through.
My name's Long Swalton and I'm a graduate engineer working for Network Rail. I'm here today to teach you about switches and crossings. The most simple form of S&C is the turnout. This is a left-hand turnout. As you can see, it diverges from the main route in a leftward direction. This is how it works. In normal mode, the left-hand wheel rolls along the switch rail, and there's flangeway clearance for the right wheel to continue along the stock rail. The inside surface of the right flange is kept on course by the check rail. This restrains the wheel set and ensures it is directed along the correct route. Meanwhile, the left wheel transfers contact between the different parts of the crossing. That's where there's a high impact load. In the reverse, the right wheel rolls over the switch rail and follows its geometry. The inside surface of the left flange is guided by the check, forcing it to follow the stock rail on the new route. And the right-hand wheel makes a crossing, again impacting a load on the crossing nose.
There are many different types of switch and crossing on the network. They include turnouts, diamonds, crossovers, and slip diamonds. The type we use is determined by a number of factors, including the number of lines involved, frequency of use, and running line speed. Trains travelling at high speeds need long switches and crossings. At low speeds, such as in stations, trains can make tighter turns. Train movements across the network are set and controlled by signallers, who use switches to set routes for trains. Switches can be propelled by various devices. One of the simplest forms is a ground frame setup, a series of
Only
rods and
in
cams
England
attached
does
to
that
levers
still
and
exist.
signal boxes. These are now largely being replaced by remotely operated hydraulic and electromechanical devices.
Seen by rail sides all across the country. This is an HW2000 points machine. This is electromechanical. What we have here is your drive motor. To check the motor has done its job, over here we have an interlocking and detection system. Detection tells us when the points have completed their travel and locked. Locking holds the points in this state, so they cannot be physically moved, so when a train runs over the top, it remains in position. Facing point locks are one of the most important safety features on the S&C layout. They ensure that the points cannot be moved when set. This is important because failure to lock the switches could cause a derailment.
As engineers, we face an ongoing challenge to maintain and improve our switch and crossing assets. Trains can create large impact and lateral forces as they change course, and these forces can cause wear and deformation. Switches and crossings therefore have a limited lifespan before we need to replace them. Less than 5% of track miles are made up of switches and crossings, but over 17% of our maintenance budget is spent on them. We'll continue to research and develop new inspection techniques and material usage to increase their performance.
It's all about creating a network that's safe, reliable and efficient. It's what we do.
Remember, it's a commercial by the British Network Rail, but it's a nice introduction. I have one more video. Okay, let me see if I can get the other one going. Can you see, everybody see this video?
When the wheels roll through the frog on a turnout.
Not yet.
Not yet.
Not yet?
Not yet.
All right, let's try it again. Okay, how's this?
Wheels roll.
Can you
Yes.
see it now?
Yes.
Wheels roll through the frog on a turnout. What happens is the wheel rolls along onto the wing rail that's shown in blue here. And it rides along the wing rail until it catches the point of the frog, shown in green. Now you can see that at no point is the wheel support able to drop into the flangeway, into the gap between the two rails, because it's firmly supported on those two rails. So it just rolls along the wing, catches onto the frog point as it's handed off onto the frog rail, and it rolls through. And because of this geometry, it will ensure that the equipment will roll through the frog without any bumping or dropping into the flangeway in the frog. Now from this, you can see that it's key that the flangeway is as narrow as possible And the tread of the wheel is as wide as possible to allow that to happen. It allows the wheel to roll down the wing rail, span across onto the frog point, and then roll onto the frog without any bumping.
You can also see how the guardrail works.
A turnout built close to the NMRA specifications, or right on, as ours are in the fast track assembly fixtures, will maintain all the relationships necessary to give you a smooth running track work when you use wheel sets that are set to the NMRA specs. And most of the newer wheel sets available today, right out of the box, are compliant. However, little track work is. Now I'm also going to show you the same thing with the RP-88 or Code 88 wheel sets running on a turnout built to the same specifications. Now you can build a turnout to different specifications to work well with RP-88 wheels, but an out-of-the-box, ready-to-run turnout or one built in our fixtures might have a little bit of trouble. And I'm going to show you what's going on there. Okay, here's the same wheel set. These are the RP-25 Code 88 wheels on the same turnout. And I'm just going to roll them through, and you're going to see how with the narrower tread on the wheels, there's less contact at this critical location when the wheel is handed off between the wing rail and the frog point. We get in real tight. You can see.
I want to mention here that this is sometimes the problems you see in light rail systems. Because in a lot of light rail systems, you'll sometimes have a narrow wheel tread because you want to make sure that the wheel does not damage the pavement on particularly for street running. So a lot of the light rail systems are designed with a narrower wheel tread, this distance right over here. But then you have to be particularly careful in your frog design, in your wing rail frog design, to make sure you don't have exactly what you're showing here. See, the previous wheel set he showed was a wider wheel set where there was a lot of interaction, a lot of contact between the wing rail and the frog in the transition. Here, there's very little contact.
It's possible for the wheel to drop down in.
And that's the problem.
Now this turnout that's drawn here, being drawn on a CAD system is 100% precise, but a ready-to-run turnout or one you build yourself, there may be slight inconsistencies in it, and it may cause this wheel to drop down in there. Now, this will be especially true if the frog point isn't as sharp as it should be. Shown here is what a frog point of some of the ready-to-run track work sometimes looks like, where it's a little bit blunt, as you can see in the end. You can also get this too when you're building your own track work if you're not careful to ensure that you got the sharpest possible frog point. And where this really has an effect, especially with Code 88 wheels, is as the wheels are rolling through here, you can see that it's completely unsupported in this area. Right here, it'll bump. It'll drop down into the frog and then click onto the edge. And that little bit of bumping action can be the source of some trouble. One way that some of the ready-to-run track work gets around this is they actually will fill in the frog. The frog flangeways will actually be filled in with plastic when they cast the turnout. And this serves a couple of purposes. One, it aids in construction of the turnout. It holds everything in place. And two, it'll solve some of the wheel drop problem. And that as the wheels roll through the turnout, it'll actually roll across this fill that's in the bottom of the frog. One of the problems with this is if the wheels, if the flangeway diameter on the wheel, not the flangeway, the flange diameter on the wheel is a little bigger or a little smaller than it's supposed to be. And that can vary from one manufacturer to another. And what will happen is as the wheels roll through the turnout, you'll get a bit of a bump as it rolls along and hits on here. If the flange diameter is a little bit too big, it'll actually lift up as it comes through the frog. And if it's too small, it'll still drop into the frog. So it's not the best workaround possible.
Yeah, one of the issues you deal with putting fillers in, and again, this I see in light rails in particular, is that you end up having what's called a flange bearing condition, where the load is now on the tip of the flange. causing plastic deformation of the flange as well. And that can, if you're not designed for it, that can be a problem.
But it is used by a lot of manufacturers, and it's used for that reason. The best way to use the Code 88 wheels is to actually build a turnout for that wheel with a narrower flangeway through here. And I'll get into more detail on how to do that and the repercussions of doing that a little later on. So as you can see, that there's a definite relationship between the wheels and the track work it's running on. It doesn't matter how well you build your track work, it's only going to run as good as the worst set of wheels on your layout. So you want to make sure that you have all those wheel sets set to your NMRA gauge. And it's pretty straightforward to do. Just make sure it fits in the little grooves in the NMRA gauge, and you'll have good running track.
Okay, we're going to come back to this when we talk about frogs, because I like this as a discussion item, but I figured I was going to give you a little bit of an intro to that as well. Let me just go back here. Okay. Okay, let me go out here. Stop share. Does everybody see my slide now?
Yes.
Okay.
Yes, we're seeing.
Okay, good. All right. Okay, so turnouts, as one of the videos, I think the British video it said, talked about the fact that turnouts and crossings are very high maintenance items. I think the number he gave was between 3 and 4 times more expensive to maintain, or I think on a relative basis. I think he said the turnouts represented 5% of the track mileage and 17% of the budget, which comes out to be roughly 3.5 times. I've seen other studies that go greater than that, where turnout maintenance represents on a per meter basis can be as much as 5 to 10 times as expensive per meter than conventional track. So turnouts are very much a major issue. Now we're going to get into this in a little bit of detail right now over the next hour and a half or so. But one of the things to remember is that although we have curvature in our turnouts and our switches, we do not have any super elevation or there's no cant in a turnout. A turnout is flat. So you never introduce cant into a turnout, primarily because turnouts tend to be very, again, the street vehicles go through them at very slow speed, plus the fact that it's very, very difficult to maintain maintain cant in a switch. So again, that will generate into greater lateral curving forces, greater centrifugal forces, greater wear, all of which we're going to see. And then we'll also talk about the fact that because of the fact that you'll now have multiple rails, again, if you go through a frog, for example, first of all, you have the stiffness of the turnout in the frog area is much stiffer than the turnout than a conventional track. Again, because you have first of all, you have 4 rails. You have 4 rails here, you have 4 rails here, you have this big turnout casting over here. And that means you have a much stiffer system. You have much higher dynamic impact loads. Most of them are high transient loads, impact loads. But you see them, and you see that because of the change in stiffness, because of the lack of elevation. You have vertical and lateral dynamic impact loads, all of which contribute to a very high rate of degradation and that associated high rate of maintenance that we've talked about. Okay. So I already talked about the fact that the turnout is made up of the 3 sections, the switch, the frog, and the closure. So the switch goes to the heel block. The closure goes from the heel block really to the toe of the frog. The toe of the frog is actually out over here. So when we look at the frog, we have the toe and the heel of the frog. So the closure goes really to the toe of the frog. And then we have the frog, which goes from the toe of the frog all the way into where you separate out into your two separate tracks. Okay. And we've gone through this switch stand, which throws the points, the connecting rods, or the switch rods, which we've talked about, point rails and heel blocks. So this, again, I'm not going to, I just want to sort of introduce some of the ideas behind you so you understand what's going on. So if you look at your switch stock rail combination over here, if you did a cross section and you start taking cross sections as you go along the track, you can see first of all, your switch point goes from very thin to much thicker. And then you need a certain amount of connecting, and it needs to be, you need to allow it to properly go across the switch stock rail. So here you can see 3 different switch points. You can see the switch point up here, up against the stock rail. In all cases here, this is the thin part of the switch point. The switch point is somewhat exposed over here. Here, it's already hidden underneath it. So here, you can see the switch point is completely open out here. Here, it's partially underneath the stock rail, and here it's completely underneath the stock rail. So in most main applications, we put a bit of a chamfer into the stock rail. You can see it over here pretty clearly. Okay, so we put a chamfer into the stock rail that allows the switch point in the closed position to come underneath it and be, in fact, be protected. So then if a wheel comes into the switch, so when a wheel is coming into the switch point, ideally we don't want the wheel to smack into the switch point, which is pretty thin. So if I have an exposed switch point like this one, my wheel can hit that switch point and smack it and damage it. Whereas if it's hidden underneath it, if I'm chamfered, then it's protected. So this is an example of what we call an undercut stock rail with a switch point. It's sometimes referred to as a Samson point. But what you can see is that in a closed position, I have my switch point all protected by the stock rail here. In fact, you can see that there's, in the longitudinal direction, you can see there's a change in height of the switch point to make sure that the wheel gradually comes into here and doesn't come into an impact. Again, if this is exposed in any way, this very thin, narrow portion of the switch point is going to be damaged. It's going to be chipped. It's going to chip out. You're going to see all sorts of damage here, and that's going to ultimately result in very premature replacement. It's a very maintenance-heavy type of application. As you can see over here. So here's a good example of the kind of damage. Again, you have a thin, you can start seeing some of the damage here, some of the damage here, some of the damage here. Again, you're subject to some very high vertical and lateral, but particularly lateral impact forces, because the wheel is coming along, it's smacking into it here. So there's actually a longitudinal component. If it doesn't properly transition into the stock rail, you have this very high impact that can cause, in a worst case, you can actually see These are real switch points. These are pictures that I've taken from, or that have been taken from real track. And you can see in this particular case how far damaged the switch point is. That particular case is this whole area down here is already broken off. So that's that whole area really coming over here. That's broken off because this is very thin. Again, if I go back here, you can see how thin that section is. You can see it also over here. You can see how thin that section is, particularly at the tip. Okay, just real quickly, we'll talk about this derailment. This was a commuter railroad traveling at about 70 kilometers per hour, and the fourth car derailed in the switch point area. So the first three cars you can see looks a little bit like the Kfar Menachem derailment, doesn't it? Where you have the third and fourth cars derailed and not the beginning one. Okay, so here, this was actually very similar to the Kfar Menachem derailment in that the wheel of that fourth car actually climbed up on top of the stock rail and traveled along the stock rail. So the wheel actually climbed up on the switch point, traveled along the stock rail for a while before it fell off. And it traveled on the flange on the stock rail. And there were well-defined wheel marks in the process. So this is actually the switch point at the derailment. What happened is the wheel actually climbed over here onto the stock rail. So instead of the wheel flange continuing on here, the wheel flange was riding on right next to the switch point, got caught onto the chipped switch point, climbed all the way up to the stock rail, and then rolled on the top of the stock rail. It was actually, you can see, that because the edge was broken, the left wheel of the fourth passenger car ramped up. So there was a little bit wear in that wheel as well. And so it literally, as you can see, it forms like a little ramp here. Let me see if I can get rid of that marking. You can see it a little bit clearer. Yeah, so you can see there's like a little ramp over here that the wheel climbed up on. And then there was also a large break at the end as well. So this actually had been repaired a couple of times by welding. And because the weld switch point is much weaker than the parent switch point, most railroads, certainly most U.S. railroads now do not allow repair of switch points by welding. If you have an emergency situation, you don't have a replacement switch point, then you have to put a 20 km/h speed restriction on it to make sure that you don't generate excessive dynamic forces. Okay, and we talked about this already, switch point. Okay, another terminology. The throw of a switch point is the actual amount it moves, and if the throw is off, and if you don't completely close the switch point against the stock rail, if there's a gap between the switch point and the stock rail over here, then a thin wheel flange. Remember, we talked about thin wheel flanges in an earlier class when we talked about wheels. A thin wheel flange can force its way between the switch point and the stock rail, and again go down the wrong side, because the other wheel is going to go down this side, and then it's going to go down. So the other wheel is going to want to go that direction. If it forces its way through, it's going to go to the diverging leg, and we have our locomotive from the first slide, which is on one end on one side and one end on the other. So that's your throw, and that's governed by the adjustment of the switch machine and the switch and the switch bars, stretcher bars. Again, there's your throw. Okay, the throw is always measured, by the way, at the number one switch rod or number one stretcher bar, which is the first one coming through. I should mention that that in the vicinity of the stretcher of the stretcher bars, there are also glide rails. There you see the steel that's on top of the ties. That's where the switch point, where the switch blades move back and forth. Those are usually lubricated as well. Usually some sort of lubrication to make sure that when you throw the switch, when you move your switch points, they move smoothly across these glide rails. Okay, so I mentioned picking a point. Picking a point is when I have a very narrow wheel flange and I have a small gap between my switch point and my stock rail, which is not supposed to be there, and I force my way into it. This will always result in a derailment. And here's an example. This is an actual switch point gap, for example, that I took from I think this was in the UK as well. We were actually doing some measurements of switch points, inspecting switches, which we'll talk about a little bit later. And you can see this is about a roughly a 5 millimeter gap. It's about 5 millimeters. So you can see if I have a very thin wheel flange coming along here, it could force its way in between this gap, into this gap between the switch point and the stock rail, and it will cause a derailment every time. Now, to prevent that from happening, there are what we call point protectors. And point protectors are designed to do a couple of things, but primarily the design, let's go back a little bit. A point protector is designed to prevent a wheel coming along and just smacking into the switch point, and in some cases, picking the point, as I showed over here. So there are a couple of different designs of point protectors. And by the way, metros tend to use point protectors very extensively. So for example, New York City Transit, which has a massive number of switch points. I think they have something of the order of 10,000 switch points in New York City Transit alone. Every one of their switches has some type of protector. So this particular protector is called a wheel crowder, and it's designed to, so what happens here is I have a wheel that's coming along here. Oops, other way around. Oops, I drew it backwards. I have a wheel that's coming along here. And if that wheel is running right against the, if it's just flanging, if it's running against the stock rail, it's going to smack into the switch point. So what this wheel crowder does is it basically picks up the back of the wheel flange and pushes it over slightly. So you can see it contacts the back of the wheel flange. Actually, the back of the wheel itself, not the back of the wheel flange, the back of the wheel, and just gently moves the back of the wheel over a little bit, so the wheel flange misses the point. It runs, and I'm running along the wheel flange up here, but I don't really contact, I don't contact, my wheel flange doesn't come into contact until further back here, where my switch, where my switch point is thicker. Again, you can see the difference in thickness of the switch point. If my wheel flange impacts my switch point back here, I have less chance of chipping or damaging the point than if I impact it over here, where I'm going to do the type of switching we talked about there before. This is another type of switch point guard. This is called a house top, and there are all sorts of designs here. In this particular case, the switch point is underneath this house top. So again, it's designed to protect the switch point and prevent impact of the wheel flange on the switch, and also to prevent it from switching the pit and preventing a derailment. Okay, just very quickly, again, this is the switch point. The switch point should touch the stock rail all the way through. So we'll go back. Is a good example here. You can see the switch point is in pretty close contact to the stock rail all the way through. That's called the mating surface. Okay, point rails. So there are okay. So now we're going to go into that. There are three different types of switch points, or point rails, or switch blades, depending on what we're talking about. So again, we're talking about the portion of the switch blade or the switch point from the point to the heel block. And so I have a straight point, a curve point, and a tangential geometry point. A straight point, which is what most of the pictures I've showed you up until now, the point is straight. There's no curvature in the point. So in this particular case, both points are straight. And this has a very sharp angle, but and it's the shortest distance. It has a very short length, it has a very high angle, and you can see there's actually a transition. There's an angle between the switch point and the curved closure rail. So you're going to see a dynamic impact load right over here. This is the cheapest design switch point, which of course is why it's used, but it's also the lowest speed because it has a highest angle and has that transition. The curve point has a uniform rate of change of curvature. So it has a constant, a uniform curvature. Excuse me, it has a uniform curvature, not a rate of change of curvature, only a curvature. So it has a fixed curvature. It has basically a constant radius throughout the curve point. It has a smaller entry angle than the straight point, and it also has a reduced transition. Really doesn't have a transition between the switch point and the curved closure rail, which means I can go at a higher speed. It's going to be a little bit longer because it's now curved as opposed to straight, but it allows me to go to a higher speed going into that diverging leg of the turnout. The tangential geometry point, that basically has a compound curve. Ideally, it has a uniform rate of change of curvature. So now R varies from the entry to the heel block. So I have a different radius of curvature. My angle is different, but it's uniform changing. That means I have the best dynamic performance laterally going through from the point to the closure rail because I have a rate of change of curvature. So I don't have a constant angle. I don't have a constant uniform rate of a constant radius of curvature. I have a rate of change of curvature, and that allows me to go the highest speed through the turnout, but it also requires the greatest distance. So again, going back to my three types of points, my straight point has the shortest length, but the highest entry angle and the lowest speeds. My curve point has a longer length, a uniform radius of curvature throughout, and the reduced entry angle, so it has a higher speed. And then my tangential geometry point has a uniform rate of change of curvature, so it has the greatest length, the lowest entry angle, and the highest allowable speed. And of course, we're always talking about the speed of the diverging leg, since the speed of the through leg is actually track speed. Okay. Again, terminology rods. Here's my first rod, also called my stretcher bar in the British case, second rod, third rod, fourth rod. Now let's get back to the frog. Okay, so we showed a little video. You saw that video of the frog for a couple of minutes. As a matter of fact, before we get into the frog, now is a good time to take a break, to take our second break. So let's take a 15-minute break. Any questions on what I've done up until now before I get into frogs? Okay. You either understand everything or
Excuse me, what is a rod?
the rod is the connector bar or stretcher bar. It is the connector between the left switch point and the right switch point to make sure that the two switch points move together.
Okay, thank you.
מוט מתיחה.
Okay, so let's take a 15-minute break. Let's meet back again at, I guess it's 7, would be 15 minutes, and we'll go into frogs. Okay, so let's see if we can finish up here in a reasonable time, and that way I'll leave the last few minutes to let you ask questions about the exam next week. So let's go back. Let's continue on here. Where are we? Here we go. Do you all see my slide showing the frog?
Yes, we are.
Yes.
Very good. Okay, so you already saw the video a few minutes that I showed you earlier. So in a normal facing move operation, we're coming this way, right? We're going from the switch point to the frog. We're going from the single track to the double tracks, okay? So the frog basically consists of the frog itself consists of 3 different parts, not counting the guardrails. So I have the insert, which is also sometimes called the nose. I have the wing rails, and I have the binding rails, which hold everything in place. So you can see this is a built-up frog. This particular frog is made of well, and it has a cast insert, but the binding rails are built into it here. So you can see here that the wheel, it's exactly as I showed you in the video. So again, in fact, let's see if I can actually show you that video again. So that way we can look at that again here. You all see the video?
Through the frog on a turnout.
Does
What
everybody see the
happens
video?
is the wheel rolls along
Yes.
onto the wing
Yes,
rail.
yes.
Shown
Okay.
in blue here.
So this is again,
It
this
rides
big thing
along the wing rail
going
until it
across
catches
the wing
point of
rail
the frog, shown in green.
onto the insert of the nose of the frog.
Now you can see that at no point is the wheel able to drop into the flangeway,
You
into
can
the
see
gap
how
between
the
two
outside
rails,
of the wheel
because it's firmly
is
supported
running on the
those
wing
two rails.
rail,
So it just
and that
rolls along the wing,
transitions it until
catches
the
onto the frog
inside of the
point
wheel
as it's
hits the
handed off
insert
onto
on
the
the
frog
frog.
rail, and it rolls through.
Okay, so hopefully you see the frog again, the frog slide now again. So again, exactly. Can you all see the frog slide, right? Okay. I'm assuming that's a yes. You can see so again the wing rail, the wheel comes along the running rail, goes across the wing rail, and then transitions to the insert or to the nose. So if it's coming across, for example, that way, you have your wheel tread is running here, here, and then down here. And ideally, everything is lined up geometrically properly so that you have a smooth transition. But again, notice again the stiffness here. So again, we're going to be dealing with some high impacts, and we'll talk about that in a couple of moments. Again, you can clearly see the flangeway for the two wheels. Again, the guardrail is what holds the flangeway, and make sure you go to the right flangeway for the right direction of the turnout. Okay, so looking at it in a more accurate point of view, again, you can see the throat of the frog. You can see how your wing rails come through here. This is the toe of the frog here. Again, this is the facing move is in that direction. This is the heel of the frog. This is the frog angle, which is also the turnout angle. This angle right over here is my frog angle. We'll talk about in a few moments how to calculate it, but I think we've discussed that in a previous lecture. Okay. Now, one of the things to notice is if I look at my frog here in the diagram, you see I have the point where my two external lines actually meet is called the theoretical point of the frog. It doesn't exist. It's a theoretical point. The actual frog, though, is cut back a little bit. Why? Because if I allowed it to come to a really sharp point, it would get mashed to pieces by the wheel. And I'm probably do a number of my wheels as well. So I basically chop my frog back a little bit. So the actual point, the real physical point, is a little bit of ways back from the theoretical point. And the exact distance there often depends on the design of the frog. So we talked a little bit about we already talked about the frog angle. The frog angle, is also the frog size is also the turnout size. So a number 20 turnout is a number 20 frog. A number 10 turnout is a number 10 frog. A number 20 turnout has an angle of 1. So that means this distance is 1. This distance is 20. So that's 1. That's 20. If it's 1 in 10, that distance is 1. That distance is 10. Typically speaking, the larger the number, the smaller the angle, of course, the greater the speed. For the normal, and I use that normal in quotes, the normal range of frog sizes is between 1 in 4 and 1 in 20. Frogs and turnouts greater than 1 in 20 are considered to be high-speed turnouts. So things like 1 in 24, 1 in 32, those are considered to be high-speed turnouts. Typically speaking, you'll see metro turnouts tend to be between 1 in 4 and 1 in 10, unless you're in locations where you have higher speeds where they can go up to 1 in 20. Railroad mainline turnouts tend to be between a 1 in 12 and 1 in 20. Yard turnouts and low-speed metro turnouts are generally between 1 in 4, 1 in 8, in that range. So again, this would be a number 1, a number 3 turnout, 1 in 3. That's a very, very sharp, that's a very large angle. And as a result, that's going to be very low speed turnout. Okay. So we talked about the difference between the theoretical point and the actual point. So let's make that point very clear here. You can see the theoretical point is where I theoretically have my intersection. If I drew a tangent line from my nose of my frog out to where they intersect, that's the theoretical point. The actual point, as you can see here, is cut back because again, we don't want a little point there. And again, you can see the wing rails and the rail that hold everything in place. So this is what really happens to a frog. Typically speaking, the life of a turnout can be of the order of 1/10 to 1/20 the life of rail in normal track. So a frog, so if I have rail in normal track, I can expect that rail in normal tangent track, that rail can last 1 billion gross tons cumulative. Hopefully you all remember what I mean when I talk about 1 billion gross tons cumulative gross tons. If not, remind me, interrupt me, and I'll explain it again. But basically, normal rail can last 1 billion gross tons if it's straight track, well maintained, etc. A frog or a switch, if it goes to 100 million gross, 100 MGT, 100 million gross tons, which is 1/10 of 1 billion. So a rail will go to 1,000 million gross tons. A frog will go to 100 million gross tons if it's well maintained, or in circumstances such as this, it can go down as low as 50 million gross tons and require replacement. So again, this is why we have these high maintenance costs associated with a switch. You can see the frog. You can see the damage to the frog. This is all due to high, primarily vertical impact forces. You can see this is the nose of my frog right over here, or the point of the nose of the frog. Sorry, the actual point. You can see the plastic flow. You can see the batter here. Look at the high contact stresses and wear in my wing rail. You can see where the wheel is running, but you can see how it's worn down, by the way, through here. And you can see now, one of the things you can, one of the other things you should be able to see here, and this is a real issue with switches, I don't care where you are, particularly with frogs, is although theoretically my wheel is supposed to go and transition over here, you can see from the condition of the nose of the frog, I've had more than a few wheels coming along and smack me right along here, either with the wheel flange or with the wheel tread hitting with a very high impact forces. Now you can see, just looking at this frog here, you can see that the bulk of the traffic is going that way, because I have a lot more damage here than I have here. So most of my traffic is transitioning from here to here to here. Well, so again, this may be, I can't tell, this may be the straight leg of the turnout, and this is the diverging leg, and if that would be the case, the bulk of the traffic would be on the straight leg of the turnout. Now, one of the other things we should mention,
Maybe the angle is bad.
well,
The angle.
the angle may be bad, the guardrail location may be off, and the wheel is not. I would bet that you have a problem with your guardrail location here. Your guardrail dimensions are not right on, and so the wheel is moving a little bit too much from side to side and impacting too much.
Okay.
This would almost certainly be a shorter angle. No, not true. I was going to say this can be a small, sharp angle turnout, but no, this can be. I've seen these on number 20 turnouts, which are seeing a lot of traffic, and I've seen this kind of damage on number 20 turnouts as well. So theoretically, the speed should match the turnout size, but you're getting very high dynamic impact forces here. So the other point I was making was a depressed nose. So in a frog design, if I'm looking the sideways, I actually want to dip the nose a little bit on purpose. So my nose, this is already battered a little bit. You can see the plastic flow, but you can see the nose is dip. So there's a vertical angle from the tip of the nose to to this point back here where it goes straight. So here's my standard guardrail. You can see my frog. My frog is back here. You can see the frog right over here. And you can see my guardrail. Notice my guardrail is picking up ahead of the frog. I want to start controlling the wheel rail contact location theoretically before I even get anywhere near my frog. I want to be all the way back here and start controlling my wheel rail contact with my guardrail. Now, we talked a little bit before, we mentioned the fact that the guardrail dimension is critical. Well, which guardrail dimension? So there are actually two major dimensions. So let's look at our scenario here, okay? So make sure everybody understands what we're looking at. We have our running rail, which is this guy over here. We have our guardrail, which in this picture here is slightly higher than the running rail, which is over here. And you can see here it's a little bit higher as well. And then we have our flangeway. So we have the one flangeway and we have the second flangeway, right? We have two openings. So I have my running rail, my guardrail, my frog with my two flangeways, right? This is my wing rail over here. And this is my wheel over here. Okay, so what are my two critical dimensions? My two critical dimensions are basically remember, this guardrail is designed to make sure the wheel goes through this side. So this side is controlled by the guardrail on the other side. So I have two sets of measurements. I have this flangeway dimension with this guardrail, and I have this flangeway dimension with that guardrail. So I have one measurement from the inside of my guardrail, which is also the back of my wheel flange. But if I'm measuring it in track, I'd be measuring it from the side of the guardrail, and I'm measuring it to the inside of this flangeway. And then I have a second measurement from the inside of the guardrail to the outside of the flangeway. Why am I doing that? Because I can get batter and degradation and wear in my flangeway as well. So if I go back here, I can start seeing plastic flow, for example, come out over here. And that plastic flow would affect that dimension. If I had plastic flow here, it would affect that dimension. If I had plastic flow here, it would affect that dimension. So these are my critical dimensions for my guardrail. The most common type of frog that's in use in modern railway systems is the rail-bound manganese frog. This is a mainline frog. It's the most expensive frog. This consists of a casting, a single casting, which includes the wing rail and the nose of the frog. And the casting is usually made out of a manganese steel, which is a harder steel than rail steel. Why do we do that? Because it's subject to greater impact forces. So we're concerned about impact forces. And in fact, in some cases, the frog is even explosive hardened. So remember, we talked about rail steel is always less than 400 BHN for the hardness of the rail. Frogs are always greater than 400 BHN. They're harder than the parent rail. And the reason, again, is we have this batter issue that we have to deal with. So the rail-bound manganese frog is the most common one. Again, uses the casting that includes the nose of the frog and the wing rails. You also have a rigid bolted frog. They showed this in the network rail video that we showed it here. As you can see, the rigid bolted frog is actually assembled out of different pieces of rail or rail steel and then bolted together. So you can again see, if we look over here, you can see that even the frog itself is not one piece, it's two pieces bolted together. The wing rails are bolted together to it. The flangeway is controlled if there's some sort of gap, there's some sort of block down here to control the gap there. This is all bolted together. So you would have through bolts all the way through this underneath here, bolting everything together. Now, if you're in a very, very high speed environment, so now all of a sudden we're back into frogs that are greater than 24, and in some cases frogs greater than number 132. We introduced the swing nose frog. Now this, for example, first of all, notice this is an equilateral turnout. You notice that the angle is the same for the left and the right rail, for the left and the right track. Okay. Also note that there's no gap here. what happens is this piece of the frog is movable. And so in this position, remember, we're looking at the frog, we're not looking at the switch point. In this particular situation, the wheel is going to go into the right-hand track, because you can see the flangeway for the wheel is open down here. If I wanted to go down this track, I would have to swing this over, and then I would have a gap that allows me to run down this track. I would swing this over, I would swing this over, and I would have this direction blocked. Actually, I would just swing it all the way over here, and that would block the direction. And I would have my wheel coming down this track here. Now, swing nose frogs are very effective, but they're very, very expensive, because now all of a sudden I need a whole new set of swish machines and gauge rods and switch rods, all controlling the frog and matching it and sequencing it toward the switch, because I have to have the frog and the switch in the same position. I can't have my switch moving to a right-hand move and my frog for a left-hand move. If I'm going to a right-hand move, both my frog and my switch must be lined up. So you can see all of the mechanisms that are associated with a swing nose frog that you do not see in a traditional frog with a double gap. But this allows you to safely operate at a high speed without worried about going down the wrong track and having a derailment. Another frog that you'll see usually in low-speed applications in yards, even though I've seen these in metros as well, is a spring frog. Now, again, this spring frog sort of looks a little bit like the swing nose frog in that it's open, it blocks this gap, this opening, and it's designed to allow most of the traffic to run in this direction. But what happens with a spring nose frog is, if I'm coming in this direction on this track, my wheel flange comes into this gap over here. You see this gap opening between this this rail and the rail going into the nose of the frog. I'm going to say this is an extension of the wing rail. It's not really, this is the real wing rail, but this is the left-hand wing rail. This is an extension. And so what happens is this wheel flange forces open. This is spring loading. These are springs over here. And this wheel flange will literally force this rail over and force itself through. And then when it goes through, it closes again. These springs close, force these rail close, and it's back in this closed position. So a spring frog is only used if there's a dominant direction of traffic and there's an occasional traffic going in this direction that requires access to the track, that requires movement. Now, another type of frog, which I'm not personally a big fan of it, but I'm seeing more and more applications of it, is what's called a flange-bearing frog. Now, in this flange-bearing frog, notice for all practical purposes, the wing rail doesn't come all the way through. In fact, there's a big gap between the wing rail and the nose of the frog. And what's happening here is, as it comes through, this filler over here raises in height and forces the wheel to run on the flange. And so what you're seeing here is your wheel flange marks. These are my wheel flange marks. I'm actually running on the tip of my wheel. I'm running right over there. And I'm running that through the frog. Now, the problem with this is this puts a very large amount of stresses in the tip of the wheel, and you end up getting plastic flow and potential failure of the wheels. But if you only have a couple of them throughout, you may not cause catastrophic failure of your wheels. So again, I see these more and more, but I'm not a big fan of them. Okay. Just very quickly, let me just show you a few more applications. This is a typical ladder track and a switch. We talked about that. So these are all switches on switches on switches, all designed to have parallel yard track. This is a crossover. I think we talked about this in one of the earlier lectures. So this is a simple, this is basically two switches or two turnouts. Two switches, one frog, really. So you can see I have a switch over here, and I have a switch over here, and I can go from this, I can go in this direction to that track. I can go in that direction on this track, but if I only have a single crossover, then I can go, if I'm coming along in this direction, I can't get over to this track. And if I'm coming along in this direction, I can't get over to this track. I would need to have a mirror image of this of this crossover in the opposite direction to give me full capability. So that would be a double crossover, which is what you see over here. So this is a single crossover, which only gives me limited movement from one track to another. This is a double crossover. So here I can go from this track here, from this track here, from this track here, from this track here. And of course I can go straight in both tracks as well. So I basically have 6 combinations of movement that I can have with double crossover. But the penalty is, whereas in a single crossover, I basically have, actually I have 3 frogs. I said I have 1 frog. I actually have 2 frogs, one there and one there. Here, I have 1, 2, 3, 4, 5, 6 frogs in this design. Real quickly, a crossing diamond is when I have two tracks that cross each other at grade. I do not have a switch in here. I do not have the ability of moving a vehicle from one track to another. Not that they can do a 90-degree turn here, but in this particular case, I have one track crossing the other track, and I basically have the equivalent of 4 frogs. They're not really frogs; they're diamond crossings, but they basically were allowing 2 rails to cross each other. Here you can see a switch going into a crossing diamond. You got a switch here, you got a switch here, and I got a crossing diamond over here. This is a double diamond. This is one of your worst maintenance nightmares you can ever run into. If you're doing track, you sometimes have no choice in designing this, but if I have 2 tracks in this direction and 2 tracks in this direction, I have this monster. So I have basically, I have rails cross each other at 16 locations. This is one of the biggest maintenance headaches in the infrastructure world. Okay, speed through a turnout. Speed through a turnout. Oh, this is the, sorry, this is the metric version. Yeah, this is, yeah. Speed of the turnout is actually calculated from the unbalance equation. If you remember the, okay, this is the metric equation. Sorry, this is the metric equation. So this is the speed in kilometers per hour R is the radius of curvature in meters. U is the allowable imbalance, and E equals 0 because there's no elevation or there's no cant in a turnout. And these are pretty much tabulated. I'm going to skip a couple of these. Sorry, I have, these are all in miles per hour. You're going to have to excuse me. So we'll convert it to metric in a moment. But you can see I have straight points, curve points, and tangential geometry points. And so, again, the standard turnout ranges, I said, were about 5 to 20, 6 to 20. So if I took a number 12 turnout, which is a common turnout, has a 22-foot switch point. So that's what? That's roughly 7-meter long switch point. A conventional turnout, either right hand or left hand, allows me a speed of about 27 miles per hour, which is a little bit over 40 kilometers per hour. Let's say 43 kilometers per hour. If I had an equilateral turnout where I'm going in either direction, I can go 38 miles an hour, which is about 60 kilometers per hour. By the way, this is why we use equilateral turnouts. But again, this is with a straight switch point. If I take the same turnout, same number 12 turnout with a curved switch point, so this has a constant radius of curvature. So first of all, my switch point goes from basically from 7. So you can see my speed is going up to about 29 miles an hour. My equilateral turn is about 40 miles an hour. So this is about what? This is about 44, almost 45 kilometers per hour. My tangential geometry turnout, I actually don't go down in number 12. So let's pick something that's uniform throughout. So let's pick a number 20 turnout, which is a common turnout. Number 20 turnout is basically 36 miles per hour, which is about 60 kilometers per hour on the lateral side. It's about 46 kilometers per hour with a curved switch point. So that's about 60, about 66 kilometers per hour. So what did we say here? So we're saying this is about 60 kilometers per hour for a number 20. Here we're talking about roughly 66 kilometers per hour, a little bit faster. No, probably around 70 kilometers per hour here. And then a tangential geometry turnout allows me to go up to 45 miles per hour, which is about 72 kilometers per hour. Where you really get your advantage in speed in the tangential turnouts is in the longer turnouts. Number 26, well, sorry, this number 20 turnout can go up to 60 miles an hour. So that's what? That's about 100 kilometers per hour. So depending on the length of my switch point and the length of my lead, so this has a fairly long lead, I'm going for a number 20 turnout, I'm going from 60 kilometers per hour to 70 kilometers per hour to 100 kilometers per hour through the diverging move. The other point I want to mention is where we see our maximum forces going through the switch point. So again, if this is a facing point move, I have a large impact point at the switch point. It stays up there. And then I hit it again at the frog. So my actual maximum lateral force is at the heel of the switch point. My maximum vertical force is at the frog. I'm going to skip this derailment. And I want to close by just showing you some of the newer technologies that are being used in switches. So first of all, let me get a picture. Let me get a picture of the switch. Okay. One of the more common technologies that we see more and more is instrumentation of the switch machine itself, where we measure the closing force or the force necessary to throw the switch, and we measure the seating. We measure whether there's a gap between the point and the stock rail. So this is something that we're seeing more and more on in terms of instrumenting switch points. Some of the newer technology is also looking at using the same laser systems that are used to measure rail profile to measure the switch. And that's what you're seeing here. So what you're seeing here is a series of slices, roughly every 25 millimeters. And so this represents several thousand slices through the rail. So this would be a switch point stock rail combination, where you have the switch point here, the stock rail here, and you can see how it fits very nicely all the way through. Each one of these is an image, and you can actually measure the gap. You can measure the side, any damage to the switch point. This is, as I said, this is what some of the newer technology that's out there. This is a frog and a wing rail. There's your wing rail. There's your frog. Again, that's your direction of travel. So what you're really looking at is a series of these slices, and you can start seeing your switch point right over there. Just watch your switch point build up. And then you put together the composite views. Again, just to finish up here, because I want to leave a few minutes to talk about the exam. This is a gap. This is the gap between the switch point and the stock rail when it's supposed to be closed. And again, this, you can see how it can be clearly measured in this particular scenario. Here is where the switch point and the stock rail are not mated to each other. The switch point is hitting the stock rail at the tip, but then it separates all the way through. So this is a dangerous situation. This is a chipped switch point. The switch point actually should have been down all the way here, and it's missing. This is where the switch point, which you can see right over there, that's the second bump over here, is very high with respect to the stock rail. This switch point is not at all protected. A wheel coming along here is going to smack this switch point and damage it significantly. In the open position, the height of the switch point to the stock rail can be measured. Damage to the frog. Damage wear to the wing rail, which you can see right over there. The center, remember the wing rail has the frog basically has two gaps. If that middle piece gets too low down or the wing rail gets too high, that indicates a very high batter. Likewise, flangeway depth is not adequate. The depth between the top of the frog and the bottom of the gap is too small. That means that I'm going to run on my wheel flange, and I run the risk of wheel climb there. Obstructions, something fouling the flangeway of a frog, where switch point contact angle. This is one that's near and dear to my heart. This is actually looking at where the wheel flange is going to import my switch point. So this is my stock rail over here. This is my switch point over here. And this blue line is a wheel superimposed on that. And you can see, you can measure where that contact is. This is good contact. This is bad contact. This contact is too far down, which means probably that this switch point is too high up. As you can see, this switch point top is over here. This switch top is over here. So this is, again, this is actually a British rail, a network rail safety criteria, the 60-degree angle contact. And you can, this is actually, you can watch where the wheel contact's going through. You know, I'm going through my switch point in this direction. So you can see how my switch point is getting thicker and how my wheel rail contact is changing. Again, this is a broken switch point. What it looks like. Close-up view, you can see the whole switch point is missing over here, which you can see over here. I haven't showed you this picture before. This is a nice battered frog with batter on the wing rail. So there's the nose of my frog. That's what I'm looking at over here. And this batter is what I'm looking at over here. Again, that's this batter over here. And what you're seeing over here is over here. And cracked, etc. Okay. Before I leave this, any questions? Either I did such a wonderful job of teaching that I got every one of your questions answered, or everybody's getting tired and ready to, and just hoping maybe he's going to leave and let me finish 10 minutes early and get out of here 10 minutes early. Okay. Last chance for questions. All right. No questions. All right. So let's,
Yes.
Yeah. Do I have a question?
The test.
The test. Okay, so let's talk about the test. Test is going to be easy, I think. I've said it before and I'll say it again. All the problems that I put on Moodle for this section of track, you're going to see again. So make sure you understand how to do all those problems. I covered all the material in class. The problem with the answer and the solution is there. You're going to see those problems. Most of the test is very. If you remember my first test, which most of you did very well on, I think. My goal is not to fail you. My goal is to make sure you know the material. So the first test consisted of multiple choice questions that were questions based on the material, problems that were like the Moodle problems I gave you, and then fill-ins where I ask you for, name the different types of wheel failure, name the different types of bearing failure, and give me some examples. Everything in the exam we've covered in class, even though I will say that I deliberately put in one or two questions that are going to be a bit of a stretch, where you're going to have to think. You're not just going to be able to go through the notes and say, here's the answer, off we go. Most of it, let me put it this way. You could easily pass the test, no problem, just making sure you go through the notes. And remember, my exams are open book, open notes. You can use the internet if it'll help you. I don't think it'll help you, but you're welcome to use it. The only thing you can't do is talk to each other. You can't ask somebody else to answer the question. You can't. This is not a team project. This is individual exams. But all my notes they're on Moodle. You can access them. And you should be able to answer the questions. There are 1 or 2 questions there, like I said, they're a little bit of stretch. I did cover them in the class, but I've sort of embellished on them. I'm making you think like engineers and to put together a couple of different pieces of knowledge that I've taught you. And so if you want to get a high A, you're going to have to do those problems. If you're going to, if you're looking to get a B or a C to pass, you don't even have to worry. Now, one thing I will tell you, please try to get an answer. Don't leave things blank. I think there was one person who failed my first exam, failed because they left everything blank. I mean, half the problems were blank. I can't do anything. If I see you're trying to answer a problem, if you're not sure what you're doing, include me some work in the notes so I can see what your thinking is. Because I'm very, if I think you have an idea of what you're doing, but didn't quite what to do it, I'll give you partial credits. If you have a 5-point problem, you really shouldn't leave it blank, because then you're going to get 0 points. If you show me that you have some understanding of the engineering, I'll give you 2 or 3 points. I'm not a difficult grader. My goal here has never been to fail anybody. I'm happiest when nobody fails. Plus, it's less work for me. I don't have to do a makeup exam. If you fail, I got to come up with a makeup exam. So, save me the work and make sure everybody passes, please. If I have to give out a lot of A's, I'm very happy. It means you've covered the material. Questions? Good. You're actually going to get out 10 minutes early.
Thank you very much.
Okay, I will be online with the exam next week. So you can ask me questions and we can work on it. The exam will start at 1600 hours, same time. I told Marina to just give everybody 3 hours if they want it. I know many of you will not need 3 hours. I'd be surprised if you need 3 hours. But I know there are some of you who have more difficulty with English than others and need the additional time. So the time is available. Again, this is not a test on whether you speak English. Question of can I figure out the English well enough to understand the problems? Because trust me, when you have a real problem in the railroad world and you're gonna have to look it up, the odds are the answer is not going to be in Hebrew. The answer is going to be in English somewhere in the literature, be it the UIC standards or the American standards or the literature or the papers. So having the ability to at least understand the terminology and find your way through it is going to be very useful to you. With that, I'll let everybody, go take a breather before you go to sleep, and we'll see you all next week. And have a good week. And we'll again practice the exams on Moodle if you haven't done it already. Bye, everybody.
Bye.
Thank you.